Good evening, everyone. This is our Design Day presentation for our automated irrigation water distribution system. This is Team 21100. Our team members are Fabiola Garcia, Misael Marquez, Jesse Peña, Colton Bilkey, and Kevin Spanis. And today we will be working on a project sponsored by Bard Water District and the University of Arizona. We will move forward to our introduction. And the purpose of our project is to create a system that allows the users to interact with the information about different canals and control gates positioned remotely. The system might potentially help Bard Water District, which is our sponsor, to reduce time concerns, allowing users to manipulate gates from a remote location instead of traveling from point A to point B to open and close gates. Our proposed system will record, store, and display water level, water flow rate, and gate position using sensors. And simultaneously, the system will provide a user interface where the authorized operators request a change in water level. The system will then send a signal to the gate's motor to start closing or opening the gate to ensure that the flow is consistent through the canals to avoid any dryness or overflow.
So next we have the methods of really controlling the system. The first method was a website, and the website was designed to abstract all of the low-level items and settings that you can interact with the remote terminal unit, which is what is actually controlling the gate. The website has a lot of functionalities. It will have two types of users, regular users and administrative users. Regular users can only check system status and request a change in CFS. Administrative users have all that as well. However, they have the ability to dismiss or snooze any system alarms. All of these users will be added by some sort of system administrator. Administrative users will also have the ability to either remove a gate or add a gate as they add more gates along the way in the future. Next is the bread and butter of the entire system. The system is programmed inside of the remote terminal unit, the RTU. However, in order to interact with that RTU, you need some sort of computer. Doesn't matter, Windows, Mac, even a Linux machine. As long as it has some sort of modern major web browser, you can interact with the RTU via Ethernet. Once you're able to connect to the Ethernet through its proprietary IP address, you'll gain access to its IDE, and that IDE is what allows you to control all kinds of things. More importantly, the programming section. Here we have a picture of my laptop actually being connected to the RTU. Like I said, you interact with it via the Ethernet. This screenshot here showcases a little bit inside of the actual IDE. This IDE allows you to monitor all kinds of inputs and outputs. The digital outs, which are labeled as DO1 through 4, were what actually are controlling the motor. You can also monitor the digital ins and any analog ins, such as sensor data. This next slide here is a pseudocode example of what the RTU will be doing. This is the basis for the logic that our system should follow to open and lower the gates.
On this slide, we will show the results of us opening and closing the gates.
As the conclusion, the system allows interactions with the gates. The system allows interactions with the gates to adjust the CFS to a desired amount via a website which passes requests to the RTUs present at the gates and receives information from the RTUs about the function of the gate and its relevant measures. The system will also be capable of passing notifications to operators of malfunctions or changes to gate positions and should be capable of doing so anywhere in the county. We've conducted a simulation via Arena that demonstrates operator requests to alter the CFS of a particular gate, as well as the event of the gate opening, closing, or losing connection within the system. The simulation includes an alternate branch that identifies and monitors the water level and whether it is deemed acceptable and the request is being carried out as specified. Otherwise, the request is denied and an alert is sent to the user.
The idea behind the simulation is to give a visual representation of how an operator's request to change the CFS at a selected gate goes through the system. where the create module represents the creation of an operator's request. Therefore, the entity that flows through the model is the request. Where the assign module, that is right after the create module, assigns the attributes, gate CFS, and gate number to the request. For this simulation, the values used are for animation purposes only. The attribute gate CFS is composed of a single expression. This expression is that of a normal distribution with values that were selected due to the probability of getting a negative value being close to 50%. This attribute determines whether the request is to increase or decrease the current CFS at the selected gate, where a positive number represents an increase and a negative number represents a decrease. The attribute gate number is composed of a discrete probability for the 9 gates, where this attribute determines which gate the request is for. Next up, we have a decision module that simulates the loss of communication. If the communication is lost, then the system would alert the operator so that it may be repaired. As a result, the request did not reach the selected gate. For the rest of the modules, they mainly show the attributes were assigned to each request. I do want to emphasize that if there is a request to increase CFS, then the gate will be raised. Meanwhile, a request to decrease CFS will result in the gate being lowered. There are 2 decision modules that determine whether the water level is too low or too high. These modules serve 2 purposes in the simulation. The first is to simulate the possibility of the request to increase or decrease CFS will result in the water elevation being too low or too high accordingly. The second is to demonstrate how the system would automatically readjust the gate's position to bring the water elevation at the gate to a good level. As a result, the system would send the operator an alert that the water level was either too low or too high.
Furthermore, we would like to thank the following people and organizations that helped us and were involved throughout the entire development process of our system. Firstly, we would like to thank and acknowledge our sponsor, Mr. Nick Barr of the Barge Water District, by giving our team the opportunity, approval, and necessary funds to build our system from the ground up. Next, we would like to thank Ms. Sarah Meyer, the sales consultant at ICL, for supplying our team with a remote terminal unit microprocessor, which served as one of the most vital components and functional elements of our system, and for providing us with the necessary information our team needed to get a good understanding of the inner workings of the microprocessor. Next, we would like to thank Mr. Brian Henry, who is the engineer for the Palo Verde Water Irrigation District, for providing our team with helpful tips, strategies, and important parameters for our team to consider regarding the design of our systems. Next, we would like to thank and acknowledge Ron from Webmaster for providing our team with the foundation for our system's website interface. Lastly, our team would like to give special thanks to our professor, Dr. Samuel Peppers, for giving our team the guidance and feedback throughout all the phases of our system design process, which was a crucial part of our overall system success.
Thank you for your time and attention. And if you have any questions or concerns, you can always contact us. Thank you for your time.